We're going to look at integration by substitution. So I'm just going to introduce the basic prototype of the problem, and I want to show you an example how this stuff is really used in actually really used in real world situations. We'll work a lot of problems out like this in subsequent lectures, but I just want to get the basics down. So integration by substitution is chain rule. Notice this is very much the chain rule formula. Right? And again, even though they're functions of a single variable, they're different variables. Chain rule is composition of functions. So integration by substitution involves composition of functions. So we'll take a look at this in more detail later. But the trick here is just with the chain rule was you have to guess what the functions f and g are. And in particular, once you make the choice that you guess g, everything is set. You have everything else works out, or it doesn't. So the trick here is to make the proper guess for the function g. However, again, it does take practice, but you'll find out there's really limited possibilities. So I said your basic building blocks of functions are powers, sine, cosine, and u dx. So it really kind of sets itself up in a way. Once you do practice some problems, you get the hang of it. The definite integral version of the chain rule is here. And this is important when you want to change the limit of integration. So the definite integral version is very important when I want to change the limits of integration. And I'm going to do an example of that later. But this is particularly important for doing numerical methods. So again, I have two examples. One will just do the indefinite integral version of the chain rule substitution, and then we'll do one and I'll show you how we change the limits of integration. So here's a prototype example. Now, of course, what you'd like to do is do this without doing substitution. So the first thing is to do it the way we were doing. Try to simplify things, try to make it so you don't have to use substitution. Substitution you only try after the basic techniques don't work because there's a certain amount of work involved in this. Okay, so the first thing is, again, I'll have more formality when we start working out the problems. But I want to get rid of the power. Now, I like to do this in a preliminary step 0, and again, when we work out the problems, I'll do it more carefully. But we want to put it in the correct form. Now, I want to write it in this form for a reason, and I'll emphasize that. We're going to work out a lot of problems with this. Okay, and I have these pieces facilitated, but I just want to write it in this method. Now, your whole choice here is you have to guess the function g. Right? And what I'm going to do is I'm going to look at this as the composition of functions. We had a lot of practice with this as chain rule. But I'm going to take g of x to be the inside x portion of this. Right? And because of composition of functions, y equals g of x. Now I am going to need the derivative for the chain rule, for the substitution. So I'm just going to take the derivative. Now this has to match up. Again, once you make the choice of g, everything is set in motion. It will work or it will not work. If it doesn't work, well, you take a different choice of g and see if it works, or maybe it won't work at all and you have to try something else. But once you make your choice of g, you get the derivative, and that has to match up here. So now notice what I have. Here's the form of u substitution. This is chain rule stuff. Here's the form of the substitution. Notice what I have is I have g in the interior, and I have gx over here. Now our choice then is we have to come up with fy, right? And if this is y, right, then this is y to the 1/2. Again, we'll work out this carefully in the problems, but this is the idea. And again, hopefully you'll work them out with me. Okay, so now everything's set. So by substitution, right, we can check, right? Notice what we have here is fy of g of x. We plug in g of x, and fy then of that is what we want. Okay, so, but it does take some practice. Okay, ready to go. Now, here is the substitution rule, which is, again, it's the chain rule. It's the chain rule in antiderivative form. Here's my data, right? It's very similar to what we had before. Once I get g, I get g of x, I get gx, and then I also get fy. See, that's all the data I need from here. So, see what I have? I have to make sure I use this rule exactly. Everything has to match up. So the pieces all have to fit exactly. And really what you're trying to generate out of this is this function fy. Right? So that's here. This has to convert down to the type of problems we did in the last section. It has to. So you're looking for powers, okay, y to the power. See, it's called substitution. You're changing the variable. Really, from this integration is in x and you're changing it to y. It has to come down to powers, sine, cosine, e to the x. I mean, these are your building block functions. Constant, plus or minus, so forth and so on. So this has to be the old type of problem here on the right. So if you're not comfortable with what we did before, you have to go back and review, because if you, this always has to convert into some basic form, x to the y to the power, sine, cosine, e to the y. It has to be that form, or it's a problem. Okay, so let's then go. You see, we can handle this part on the right in the usual way. Now I was just using this notation. Okay, it's a basic problem. Okay, and so now again I'm in y's, and that's a problem. My original problem was in x, so I have to convert back. And that provides, I can check, that provides my generator. I'll be much more careful and methodical when we start working out the problems, but this is just the idea. Okay. Now, in practice, now I'm not going to test you on this, so again, just don't panic with this. But this is how we actually do this in practice, and this example offers a good example. Now, e to the x squared is integrable. It's continuous. It's bounded on this closed interval between minus 1/2 and 2, including the endpoints. So this is integrable. We have a theorem that says that. But I can't find an analytic antiderivative for this. I can't use the evaluation theorem. So what do? I mean, what are your options? I mean, this is a very typical problem. This is how it really always is. I've never had a problem where in my work that I could ever just integrate using the antiderivatives. But what do? Well, you have two options. You can make a Taylor series here, convert e to the x squared into a Taylor series, turn it into a polynomial. Yes, of course, it's not exact, but again, how accurate do you need to be? And you can integrate a polynomial easily. That's not a bad option. Or what you can do is numerical integration, i.e. do Riemann sums. Now, typically, numerical integration packages are set up for functions defined over a fixed domain, 0 to 1. And it's your job to input the function to change variables so that instead of going from 1/2 to 2, you're going from 0 to 1. This is very common in numerical packages. In fact, when I write my programs, when you do it, this is typically how it's done. You have a reference element is what you call it, and it'll be 0 to 1. So you do all your packaging, your Riemann sums or whatever you want to do between 0 and 1. So I have to convert this. I have to change the domain here. And I'll show you how to do it. Again, I'm not going to test you on this, but this is how you're going to see it. That's the issue. I want to convert it to 0 to 1. So the way I get from this side to this side is I have to change variables. I have to do substitution. Okay, so we just have to set it up. It's a different way of thinking about it, right? So here is the substitution rule. Here is basically the chain rule again in integral form, antiderivative form. And I have to match these up. Now, the issue is I need to find a function g here. All right, so again, I want to emphasize, I want to change the domain of integration from 1/2 to 2 to 0 to 1 because I can do numerical, set up my numerical package between 0 and 1 on this domain. So what I'm going to do is I have to guess the function g. Now you have a lot of possibilities here, but a linear one works fine. So this is what I have. Top is the chain rule. The bottom is my reference problem. right? So the way we're going to start out with this, and in fact, I learned this when I was coding, and in the documentation for the program I was using is how to do this. So again, this is very common if you're going to use numerical packages, and you are. I mean, you are. Okay, so notice what I have. I'm just setting up the notation. B is 2, right? B is 2. Beta is 2, right? And G of 2 then has to be 1. Right? This is what I know. I'm just matching it, right? Lining everything up. Right? I'm just lining everything up. And on the other side I have alpha is 1/2, and then G of 1/2 is 0. So these are my conditions. And I can meet these conditions with a simple linear transformation, change of variable. It's just going to be a line because I only have basically 2 points I have to match up, and the easiest way to do that is with a line. So that's the easiest way to go about this problem. Okay, so now I'm going to fit this data into that line so I can calculate the slope and the y-intercept. Okay, so again, here's my data. Here's my data. You could plot it, it's just 2 points. Here's my line, and let's just fit it in, right? G of 2 is 1, I plug that in there. G of 1/2 is 0. It's just 2 equations and 2 unknowns, right? 2 equations and 2 unknowns. So I can easily solve it for the slope and the y-intercept. Now notice this then gives me my function g, right? This gives me my function g. And once I have g, right, this is kind of the link. This is kind of the link. I have x and y variables, so I can go from x to y or y to x. I can take my derivative of g and get gx, right? And now let's go. So this is my template. This is what I want to do. Okay, so let's start. Now, everything over here has to be in the variable x. Everything over here has to be the variable y. And I'm helping to distinguish this with the color. Okay, so here we start. This is what we have, right? And I'm trying to change this. I don't care what happens to the function. I'm going to numerically do it anyway. This is what I have to change, right? So I have to get, notice the derivative is 2/3. I need a derivative in here. So I'm going to put in a 2/3 and take out the 2/3 because this is equal to 1. So I fit the 2/3 in here, right? And then this has to be, by definition, this has to be Fy of g of x. Now I know g of x here, right? And that's my derivative. Again, it has to match exactly, right? So this is what I have. I have to find what this function Fy is, but I do know gx. So here I have Fy of gx is this, right? And now what I want to do is I want to convert everything to y's, right? The variable here is y. So, of course, y equals g of x. So now I have it on this side sorted out. You can't be mixing y's and x's here, right? And on this side now, what am I going to do? Well, I have this transformation that relates x and y. So I'm just going to simply substitute in. Now you can argue this is a mess. It is, but I'm going to do it on the computer. So once I program the function, I just plug it in. It's no big deal what it looks like, right? It's no big deal. So that's my function Fyy. Yes, it's more complicated, but again, there's no free ride, right? It's pro and con. So the advantage is I'm changing the domain of integration from 0 to 1, and the price I pay for that is, yes, my function is a little more complicated. In general, they're both complicated, so it doesn't really matter. Okay, so now everything is set up for my numerical integration. So I changed the domain right from 2 to 1 and from 1/2 to 0. And that's a big deal. And again, these arrows should be equal signs. I'm trying to just show that we're pushing it along here, but they're equal signs there. It's everything that's equivalent. Okay, and that's it. This is what I then put into the numerical package. So it's an integration, so just do Riemann sums or Simpsons or whatever you want. but I just put a grid, I get it. And yes, I mean, is there some numerical error? Yes, but I can get it as accurate as I like. Okay, so this is the form I want. And yeah, that's what we do. So again, here's a typical problem. I cannot solve this using the evaluation theorem. I cannot solve this. I should really say evaluation theorem in my notation. You know it exists. You know this is a number, right? It's a definite integral. This is a number. This is typically the kind of calculation we do. And we do this. Every time you do a numerical calculation, you're more than likely doing this. And you'll see. This side of the equation, I just have a numerical package. I tell it what the function is, and there it goes. So this is very effective. If you look at the picture, instead of, see, here's my original function, e to the x squared, and here's my x variable. This is what it looks like. Clearly there's a fixed area. This shaded area shifted when I don't know, when I went to PDF form. But this is what I want. That's equivalent to the area under this curve from 0 to 1. And this is the y variable now. So they have exactly the same area. The difference is that I can do a fixed numerical package, use it between 0 and 1. And again, this is called the reference element. And in fact, as I say, this is exactly how you're going to use it. And this will come up a little more later. I'll introduce this idea. But again, don't panic. I'm not going to test this. But I'm telling you, this is in fact how we do it. And I wish we could spend some time on that.